The problem here was not the error. It was a failure of NASA's systems engineering and the checks and balances in our processes to detect that error. That's why we lost the spacecraft. These were the words of Dr. Edward Weiler following the loss of NASA's Mars Climate Orbiter in 1999. The incident was caused by a consistent cumulative navigation error stemming from a failure to convert English units to metric units in a ground-based software file. It highlights the importance of constantly checking for issues, regardless of how brilliant the engineering team behind the project is. Had NASA developed these systems that flagged anomalies before they became problems, they might have had a chance to save the spacecraft. Unfortunately, this wasn't an isolated case. After $300 million in just 37 seconds of flight, the Ariane 5 rocket exploded in 1996. The primary cause was an operand error that occurred when a 64-bit floating point number, representing the horizontal bias velocity, was converted to a 16-bit signed integer value. The velocity of the Ariane 5 was much higher than that of the Ariane 4, for which the code was reused, causing an overflow. Anomaly detection could have involved simply checking if the value exceeded the 16-bit integer's maximum range, and if so, handled the exception gracefully instead of crashing the processor. So, how is anomaly detection done? It begins with data ingestion. There are three primary methods: batch ingestion, where large chunks of data are pulled periodically; real-time streaming, where telemetry flows continuously for near real-time detection; and hybrid ingestion, which combines both approaches. Telemetry is commonly stored in CSV or HDFI files, which will be used for the following example. We begin by loading a raw telemetry CSV into a pandas data frame. Then we scan the dataset's columns for timestamp aliases, such as time, timestamp, or mission-specific names. Once identified, we convert the column into pandas datetime objects and sort the dataset chronologically to prepare for time series analysis. But at this stage, the data is still messy. In pre-processing, our clean function removes impossible values, non-numeric entries, and empty data points. After that, we remove duplicate timestamp variable pairs to ensure that each piece of telemetry is uniquely represented. This gives us a clean, physically meaningful dataset to work with. Now that pre-processing is complete, we move into feature extraction. We start with the clean long-format telemetry. Each has a timestamp, variable, and value. Using our pivot wide function, we reshape this into wide format so every variable becomes its own column. That lets us view the data as a set of synchronized time series evolving together. To capture local behavior, we slide a fixed size window across time, and for each window we compute features like means, standard deviations, maxima, and slopes. These window-level statistics capture trends, periodic patterns, and sudden shifts that aren't obvious from single data points. They also compress thousands of readings into small, consistent feature vector that models can understand. When we stack all of these vectors together, we form Feature Table X, a structured, high-information summary of the spacecraft's behavior over time. This table is what our models analyze, compare, and ultimately score for anomalies. For modeling, we have two major options: supervised and unsupervised learning. Supervised models work best when we have labeled anomalies and want to train the model to recognize similar patterns. However, in real spacecraft datasets, true anomalies are rare and usually unlabeled. This makes unsupervised learning the most practical approach. One of our unsupervised methods is k-means clustering. Here, we group feature windows into clusters that represent common operating modes of the spacecraft. If a window is significantly further from all the other clusters, we assign it an anomaly score proportional to that distance. And while we visualize this in 2 dimensions, these models can operate in dozens or hundreds of dimensions, supporting any number of features. To tie everything together, we use an ensemble of anomaly detectors. Multiple models evaluate each window in parallel, contributing different anomaly signals. Because these models operate on different scales, we apply robust normalization using the median and interquartile range, bringing all scores into a 0 to 1 range. The ensemble then combines these scores with the mean and selects a 95th percentile threshold. Windows above that line are flagged as the most likely to be anomalous. By blending information across models, the ensemble reduces false positives and highlights the regions that matter the most. We tested our end-to-end anomaly detection toolkit on NASA's SMAP dataset, the challenging benchmark containing multivariate spacecraft telemetry. With 64 channels and 25 dimensions per channel, anomalies may span thousands of timestamps and propagate across multiple sensors, making detection difficult. Despite this complexity, our first iteration pipeline achieved strong early results. Several channels reach a precision of 75% and a recall of 53%, indicating the model can correctly identify the majority of true anomalies while keeping false alarms relatively low. Future improvements include expanding cross-channel features, refining ensemble weighting strategies, and incorporating more advanced temporal modeling. We can also improve the pipeline through adaptive windowing and more robust physical constraints to reduce false positives.